It got moved yet again. Hey, it's Coffee Compiler Club. Here today to talk about compilers and maybe sea of nodes and memory layouts and why does Zoom keep changing their button layout so I can't find the record button and heaven knows what else is going on in the world. Everyone's being recorded. Hopefully I get it up on YouTube within a few hours. And then Levo wanted to open to the question. So I guess go Levo.
Okay, so I don't really care about formatting, but I know a lot of people do. I don't plan to write a formatter for Bolin, and you guys know I'm writing a text editor. So I was just wondering if there's like a language agnostic, like pretty printer or formatter or something like that.
Language, just a general purpose.
Yeah, something that supports C like languages, like things with braces.
There's a bunch of them. C Beautifier, and then that's very old, but there's a lot of these things. Yeah. Yes, they
Clang,
exist.
Clang format works with multiple languages.
But probably
Okay.
not the one he's just building right now, right?
Look for something called Open's algorithm. I know that Swift uses this and at some point Rust, I think.
Well, I don't want to implement it. I just want some library or some executable to
Mm.
call.
What I'm thinking is maybe you have some kind of standardized AST or CST format. I remember that there are like other tools that use some kind of common CST format, and then they can show you nice trees in a browser, and you can click around them. And I could imagine if you implement this format for other purposes, it might be possible that there is a formatter already that can work on this JSON CST thingy that is used for the browser rendering. Maybe that's something to look into.
I found a very old link. If somebody has a better one, please throw it in. Oh, there it is. That's the one. No, I have a newer link, but I don't claim it's because mine's from 87 and not 79, but I don't know that it's any good. And welcome back, Flavio. It's been a while. Divinda, do you wanted to talk about chapter 10? This was see if nodes doing memory things.
Yeah, just give me 2 minutes.
Give you 2 minutes, fine. Are you going to share screen? But I'll turn it on anyhow.
I will, yes.
Yeah, okay. Yeah. What other things are going on? I've got my AAs doing mutual recursive letrec automatic discovery thing working so I can get mutual, I can get let recursive style type inference, but C style, write your code in any order and it sorts out what order things go in, finds all the forward references and patches them up the obvious way. I don't know, that was not a big deal. It's a pain in the neck. It was a lot of stupid small shit to do. Basically cycle discovery on definitions, but
You did that on the AST side.
yeah, because I was trying to sort out. I still maybe I'm closer now. I as of 2 weeks ago, I was still running into bugs where I had self-recursive definitions sort of coming out by default because of I'm trying to integrate the stack frames and structs as the same thing. They're implemented the same under the hood. I had some funny places where I was picking up recursive self-definitions access from the stack frames as an argument to a function, and the functions being defined in the stack frame. That was leading me to types that were incorrect because I had, in the Henry Miller, you have to have a certain point where you do you make a fresh, you let polymorphism, you get a fresh type. And I wasn't getting it in the right spot and tangling myself into big cyclic knots. It was a pain in the neck. The switch to the AST removed one level of confusion from my algorithm side of things and let me sort out the problem. And then
So-
I may go back and drop the AST once I get it sorted, but I'm going to do more robust testing before I quit or give up on the AST or make that decision one way or another. So I can clearly do like stupid looking code. I have some ugly example I could throw down. I'm stalling for time, but I'll throw this ugly example out as soon as I find it here.
So maybe this is some of the things that are easier representable by the AST, but easier captured by
Easier to
syntax.
capture the notion here. Let me go share the doc, show you the kind of thing I'm looking at. So hopefully people can see that. So I define A as a function which takes some X, calls E, and then chooses between B or B of X or X. Then D calls E, chooses between B or C of 1 or 2. Then C calls A and B calls C, and E is just randomly a Boolean of 0 or 1.
Can you drop the screen down a little bit?
I'm
the
sorry,
share.
say it again. Sure.
On the share, we don't see the text.
Oh, it's not in the. My
Yeah.
window is not the same size. Is that better?
No, it's fine. No, it's fine.
Okay. So if you look at this code, E kind of stands alone. It just returns a random true or false. A, B, and C just call each other recursively, doing nothing with X except passing it along. So they're a mutually recursive identity function. D picks on, calling either B or C with some int. And then I also call C down here in my result. So the at struct down here says, I can call it with a float, I can call it with an int, and all I'm doing is showing that ABC as a set taken together is a polymorphic version of the simple identity. It's a hidden identity function. And I wasn't getting this right in the stack frame. So the ABCDE here along the left-hand side, that's actually implemented as a stack frame, as a struct, as a normal struct. And it's middle of definition. There's a hidden struct there. You're in the middle of defining that struct. You've defined an A, and then you defined a D, and you defined a C, and so on and so on. Somewhere when I get down to the point of defining E, I discover I have enough information to realize that the ABC closed cycle doesn't include E. E is referred to from outside the cycle. Therefore, ABC taken together is a mutual let rec. And as a mutual let rec, it's let polymorphic in all of them taken together, and that makes it an identity call. It randomly go around the cycle on the identity based on the random number, or it returns the identity. So that was a kind of a screwy thing to go set up. That was what I was having trouble getting this in the straight up C of nodes declaration, because of the time I'm parsing like A there, and I go through and I find an E, it's a forward reference. I find B, it's a forward reference. But to make it a Hindley-Milner style let rec, I need to know the set of available in progress definitions. So actually, a better example is go to line D here, and in the middle of parsing line D, and I come across a call to B. Now, I haven't seen B yet in the parser. I don't know. So is A's definition done at this point? Well, A has some forward references. So I don't know if A's definition is done or not, because it has to have its entire reference set available to it.
Do you mark it in progress?
So A needs some way to mark it in progress. And when it's in progress, the use of B here, the highlighted one inside of A, will be not let polymorphic. And the same for when I define C here and call A, and I call B calling C, it's because it's in progress as a set, it's not let polymorphic. But the call to C down here at the bottom, that is let polymorphic. So the ABC combo is now a polymorphic free type variable. Therefore, I can make it a float, and I get a float back, and it's all good. So I can't tell at the time of parsing if you're part of you're a closed definition or part of a let polymorphic set. And if you are part of a let polymorphic set, I have to hold on to more information. If you're in the middle of a cyclic definition, I don't need any more info. But if you're outside, I need some more info. And I wasn't figuring out which is the right info to collect. So I kept going round and round circles, and several things happened along the way to solve this problem. One of them was I got a better set of test cases that more clearly only failed because of not doing this correctly and didn't have other failure issues. So
one thing comes to mind in more than your market in progress, you're recording on who the code is blocking. So this definition is blocked on this definition.
right. So at the time I record B as a forward reference inside of A, I need to record in the forward reference that I'm a forward reference inside of A.
Mhm.
Then when I come down to this B here, I have to say, oh, this B is also the same forward reference. It's inside the def for D. Now, I don't know if D is part of the closed cycle that A calls B, calls C, calls D or not. I can't tell yet.
Mm.
And then I would record again, for C, record for A, record for C here. When I hit the definition for E and it finally closes, E is outside of the other definitions. So I'm done with all the forward references for A when I complete E. And now I can do the closed cycle thing and declare it's an ABC. And because it's an ABC as a separate thing, so then you do a cycle finder and reorganize. And what I do is I do a cycle finder, reorganize the AST tree into a set of nested trees, except the let recs are held together.
Mhm.
And now I can do a classic Henley-Milner on them and get the right type and walk away. And I can obviously translate this to CF nodes directly, but sorting it out was more convenient this way.
Mhm.
So that's how I ended up with that. And that was sometime last week. And out of that came the other places where I had cyclic definitions that were killing me. I think I both know what happened and I now know how to solve for it. So I may have solved these problems been plaguing me for like 6 months and I kept them coming and going
It's
and
a
coming
nest.
and going, but never quite understood it. Now I think I got it.
The cycles I have seen, they are represented how they represented the cycles in a graph. So that's how they discover the definitions depending on who is depending on who.
I'm sorry, who's doing this?
There was some article when I don't remember right now. I will share
Okay.
the link when I remember.
I mean, I eventually just do a classic cycle finder.
So yeah, that's boils down to,
Okay.
that this is boils down to, yeah.
Yeah, okay, fine.
Because there are some tricky issues with the polymorphic definitions, how polymorphic they are, and their techniques to restrain that polymorphism to intersection types. So they're yeah, because that can cause problems pretty quickly with the polymorphic levels increase. How polymorphic something should be.
Yeah, I don't think I'm doing any intersection type. There's nothing to do with the intersection.
No.
What? Yeah, okay. Right. So they had an additional constraint.
Yeah, the thing boils down to how I think how polymorphic it should be, and there are sometimes that being polymorphic actually gets you into trouble. So they're trying to restrict that to boil down, not to too eagerly go to a polymorphic type, but they represent it as a intersection type as long as the types are a few maybe, and then if there are no other way, then that's the polymorphic type is the principal type, the definition.
Okay.
Oh yeah.
Yeah, I'm just standard Henley-Milner. Let me check with Dibyindu here. Are you ready to go?
Yeah, sure.
So Lilo, save your question. I'm sure we'll have time for it. We got our time. And I think sharing's on, so you should be able to screen share.
Okay. Let me know if you guys can see.
I can. Let me go widen. Although I ask for a light view for the video.
Okay.
So a light theme or whatever, however you want to call it.
Yeah, okay.
You go up on probably under view at the top, menu bar, appearance, yeah, somewhere you're doing it this way. Oh, interesting. Darkula, no, go to IntelliJ Light, yeah. Boom, yeah, okay. Yeah.
Okay.
Thank you.
Just a second. All right, so so I wanted to talk about what we are doing in chapter 10. Essentially, until now, in simple, we have values which are like register sized. So SSA values, but basically SSA because they're just register size, so they don't occupy more than what one register would. But now in chapter 10 we are introducing structs. So structs are obviously not going to fit onto a register, right? So we need memory for that. So therefore in chapter 10 we are introducing the concept of memory and how memory works in Sea of Nodes. So it's interesting because I had very little idea about how this works at the beginning. And we had a session, I think in CCC of maybe 2 or 3 CCCs ago, when we discussed and we kind of said, okay, this is what we're going to do. And so now I've kind of gone and done some work on it. Okay, so I'm just showing you here the README file for chapter 10, just to give you a starting point. So the core ideas of memory are that, and correct me if I'm wrong anywhere, Cliff. So the program starts with a single memory value, right? That encapsulates the whole of available memory. So imagine that as you start your program, you have all the memory available to you. Now, what we do in Sea of Nodes is we then, as you have struct types created or registered or whatever, as you're defining your types, each type kind of carves out a piece of memory because we do type-based alias analysis, right? So that means that each type essentially, and why we carve out this memory will be clear in a short while. But basically each type, you can imagine that each type actually carves out a piece of memory. And we don't even, we go granular than that. Sorry.
It's not a type that carves out, it's a field of a struct.
That's right. So I was just going to go into that. So it's actually more granular than a type, right? It's actually going down to the field level, right? And what does that mean? So here's a simple example. You have 2 structs here, right? And they have 3 one has 2 fields and the other has 3 fields. You can imagine that what we will do in simple is that we will assign an alias ID to each of these fields. Now, in this case, we don't have inheritance, but if you had inheritance, then aliases would be shared between subtypes and supertypes. That's right, Cliff, right?
Yeah.
But because we don't have inheritance, so what happens is that these XYs do not share any alias, and they each get individual alias numbers, right? Why is this important? Why are we doing this?
Hang on. You have chosen suggestive names that inheritance would be useful here. But if you're trying to just show it's all different, you could have picked names like vector 2D and something unrelated, animal, person, cat, for the other one. They don't have any correlation, and the vector is a suggestion, but it doesn't carry any meaning at this point.
True. In fact, I deliberately chose same names because I wanted to show that even though the names are the same, they get different alias numbers.
Yep.
Right? Because that was my point, that we are not sharing the alias numbers for X and Y, even though they appear in these 2 structs. So why is this important? I guess it's going to be easier to understand this if we look at, now we go into this diagram, right? So we have a piece of code here, right? So you have a struct declaration, and then we declare a variable of that struct, and then we are accessing X and Y, right? So we have a store here. Store is when you assign a value. And we have another store here. We have another store here. And we are returning V. We don't have loads here, but we could have loads as well. Load is when you access a particular field, right? What is important to see is that the way we are setting the aliases up is that from start. Now, as I mentioned to you, that at the beginning you have.
Hang on, Dibyendu. Somebody was trying to say something or ask a question.
Yeah, where does the arg come from in that example?
Okay. So Cameron,
Yeah.
your sound is very low. If your mic is weird. And then go Dibyendu.
Okay, arg is a single argument input to a simple, because simple doesn't have functions at the moment. and we needed to have an argument that comes from the outside world. So what we did is we provide a single argument to our, you can think of this as the main program, right? We just
Yeah.
have a main program. We don't have any subroutines or functions at the moment. And you
Nope.
receive an argument from the
No function
outside.
signatures, so you can't declare multiple arguments. You get
the
one
moment.
free, it's like calling main, we get an array of strings. Here, main gets called with a single integer, and that's all it's allowed.
That's right, at the moment. We will extend this in the future once we have functions and things like that. Okay, so start, as I mentioned, so what happens when you start your program, you have all of memory, right? And then start kind of gives you
Hey,
here.
Bindu, go ahead and
Yeah.
scroll and get the whole picture on, and then quit scrolling while you explain, and maybe shrink your bottom run window so you can see the entire graph.
Yeah. Can you see? Or I can switch to, yeah, I guess I could switch to this. I don't know if that's better or this is better. Can you
I
see
think
the
that's
whole
good.
graph now?
Can people see this in its entirety? Okay. Then let it
Okay.
ride and don't move it so people can stare at the graph without having their eyes try to catch you scrolling
Sure.
up and down.
Yeah, sure. So start gives you certain things, right? So for those of you not familiar, start gives you the control flow. So you start with this control, which is what control, which is the control flow, and you can see the red arrows, right, which is showing the control flow. So ignore that for the moment. Start gives you the argument you received from the outside world. And now these are basically not, these are aliases, memory aliases. So because we declared a struct with two fields, X and Y, start is giving you two slices of memory. One is for vector 2D X and the other is for vector 2D Y. And what happens is that every load and store on these two fields for this struct gets threaded, so that you can think of it like there's a single thread going on. So what happens is when you first do the store, as you can see, the store points to the alias X, and it produces a new version of this. And that is then used by the next store. So every time store is kind of producing a new version of your memory, right? Of that aliased memory. So all the stores are being threaded for that single field for that struct. But what it means is that if you have other stores happening on another field of a different type or the same type, they can go in parallel, right? So they're not being single threaded, if you see what I mean, right? So
Yes.
essentially, it's giving you parallel streams of execution, but at the same time, it's making sure that if you're trying to update the same field, then it's all sequential.
Is it
Then you have an order.
Is it a special kind of edge on the graph? Because I see there are edges that are data edges, just the operands for stores, and this one is memory edge.
Yes,
Are
yes,
they...
we will. We have to color this green because these are memory edges, right? Yeah,
The edges
right.
are not otherwise special. Their implementation is the same as any other edge. It's merely a pointer in the store node pointing up to the projection of $vector 2D there.
Right.
But it
So
happens
the
to carry a memory
multiple
value instead of an integer or a pointer.
the multiple store nodes here are different versions of stores of X's and Y's. So
Yes. So what's happening here is that when you create a vector 2D, we have an implicit store of 0 on each field, right? So there is an implicit store happening
No,
at
it's
the
an
beginning.
explicit store. You have explicit.
Oh, okay. Yeah, sorry. What I mean by implicit is generated by the compiler, like
Okay.
you're not coding it.
Okay.
So it's basically saying it's generating this instruction to store 0 onto X and store 0. So this store is also storing 0 to Y, right? So there are two stores which are generated by the compiler, and then you have subsequent stores happening 1, 2, and 3, and you can see them. 1 is being stored into X, right? And 2 and 3 are being stored into Y.
So the highest value holds the freshest version, the current version of this store.
The down
Or the
Highest
lowest.
value.
Or the lowest. Okay.
The
No,
lowest.
so
Down the screen
yes.
has the most current values as you roll forward. Yeah.
Okay.
Yes.
Okay.
So essentially, you can think of it like each store is using, these are the uses, right? So it's using this and it's using this store. So you're always looking at users, who is using what, right? So in these arrows, okay? So it's not showing you the control flow, it's showing you who's using whom, right?
We need to get the color fixed, and make it easier to see memory edges.
Yeah.
So one of
Okay,
the
and
things.
so
So
then
to-
the other thing I wanted to, sorry, other thing I wanted to mention is that because these are just nodes in the graph, so these are projection nodes, right? And they are just symbols in the symbol tables, but they start with this $sign so that you cannot directly access them in your program. So imagine that these are variables declared in your program, but you can't see them because they start with a $sign. And $sign is not a
Let me
valid.
put some context in here. You're
Yeah.
parsing. During
Yeah.
parse time, these aliases are available. They're effectively treated as a kind of a local variable that got declared on your behalf when you said new vector2.
That's right.
And now it's just another local variable from the parser's point of view. The parser doesn't give a whit where it came
That's
from.
right.
So it's cloned by however you clone control flow and ifs, and whatever the parser does with local variables, he does with these two, and he's doing it with memory. So
Exactly.
there's no extra technology in the parser to deal with the flow of memory directly. There's extra technology to declare a new thing. There's extra technology in the parser to do loads and stores for field updates, but nothing about the actual carrying around of the values. They're just another value, just like I
That's
had a
right.
local int variable.
That's right. So the advantage of that is then you get things like phis for free, right? Because these are just there's a phi here where we are getting two memory slices, and there's a phi function, right? And you're getting that for free because we're just utilizing the standard framework of CF nodes, right? So that's the beauty of doing it this way. I suppose aliases could be done in other ways, but I wanted to do it this way because it just utilizes all the machinery we've got, and we don't need any extra machinery, right? So the other point I want to mention is that the start gives you all of memory, and so everything starts from there. And conceptually, return is where you gather all the memory back at the moment. In the future, in simple, we will have special areas of memory being split and merged, but we don't have that right now. Like when we have function calls, we'll have that. Right now, we don't have it. So right now, what happens is all memory is then gathered back in return, right?
Let
So return.
Let me add some color to that. So
Yeah.
scroll up a tiny bit so we see start and return together. Conceptually, always start produces all of memory. The exit of the program gathers all the memory.
Yeah.
For various kinds of efficiency in different
Oops.
places, you want to think about it as that conceptual thing. It produces and collects it, but maybe I only care about some set of aliases in some piece of the program, and all other aliases I don't care about. So I want some short form that says, these are ones I'm interested in, and here's all the rest, and they just flow through straight up and I don't touch them. And that's the thing with that one is it lets you get efficiency back because you don't have to declare every possible alias in every compilation unit all the time, everywhere. You get a huge count of edges that are just, the return has, every possible field mentioned. I have 1,000 fields mentioned, so it has 1,000 edges. No, there's a shortcut for that.
Yeah, and I'm hoping that our peeps will get rid of them, right? Once they're not that are not used.
I wouldn't even make them Debian do, as I'm saying.
Okay.
They don't have to ever get manifested and then removed. So if you want to talk about some of the peeps you could do here now.
Yeah, so before I do that, I just wanted to also mention that what was I going to mention? That you can see here the new pointer. So there are a couple of things we needed to have we had quite a bit of discussion, and we weren't sure exactly how we would do this. The new here, as you can see, has an edge to control. And we had a fair amount of discussion about this. The reason for doing this is to anchor the new in the control flow. If you don't, so new basically gets anchored to wherever my current control is. So if you had a new inside an if condition or a while loop, it will point to the control flow of the while loop or the if condition, right? And this edge essentially is anchoring the new, right? But conceptually, you can think of it like new is actually because this is whole of memory. So new is actually, also kind of saying, oh, okay, I'm, looking at the whole of memory. I don't know if I explained that very well.
Yeah,
But,
let me make a different. So when we looked at this a couple weeks ago, what really comes around here is that there's like a bunch of semantics you want to cover, and then there's a bunch of ways to slice and dice nodes to cover it, and they become more or less convenient in dealing with the nodes, depending on how you slice it. So don't think of this particular slicing as the only way to draw or deal with memory in a sea of nodes kind of situation, but it's a way. And this particular one, using control on a new, pins it in a control spot. It has nothing to do with memory. You're saying it's as if it's threaded on memory. It's not. At this point, it's threaded on control. You could pin it using memory instead also. You could have the new produce a memory state, take in and produce a memory state. Then it's threading through the memory. And then the stores would come after the memory state that was invented by the new.
And why do you want to pin allocations at all? Like, I can see benefit of having them actually less constrained, so you can move them out of loops or sync them.
Right. So in an allocation where you're making a new element every trip through the loop, you don't want the new to accidentally float out of the loop, because so you number in, you're making a linked list of length in. You're just saying new, and you're chaining them all together. But you can't have one allocation for the whole loop. You have to have as many as you iterated for. So now, who does the allocation and why is it pinned in the loop? So a thing to think about is you say new, people in their heads immediately go to it's doing the bump pointer, but also somebody has to say there's some memory getting sliced and held set aside. Those could be independent pieces or together. In the example we just talked about with the loop, somebody has to be threaded on memory to prevent you from hoisting out of the loop. And as I said, there's a couple ways to slice and dice it. We don't have pictures for a couple of the different slices, although we talked about this a bunch at prior CCC.
Yeah, and I think it's in the loop case, it's the fact that this allocation will be used in subsequent iteration. That's what semantically holds and requires this allocation to happen on every iteration. If you're not using it across iterations, you can hoist it over the loop and then pretend as if you have.
There are two things that happen in an allocation, so you have to be careful which one we're talking about. There's a thing that gets you a pointer. There's a thing that gets you a block of memory. There's two outputs from any allocation, a pointer and a block of memory. The block of memory is almost surely always pinned in the loop somehow, so that as I walk through a node that says set aside a block of memory, it somehow takes in the prior state of the universe and declares I have one more element in the state of memory. So in the case I've sliced it along these fields, I have a collection of vector 2D X fields. When I do an allocation, I get yet another X field in the vector 2D pile, vector 2D.X pile.
So what I'm trying to do, I understand we can't pin it and then like, yeah, it just works. What I'm trying to do is I wonder if there is a set of constraints that will make allocation hoisting like, I don't know, natural in this scheme. Because let's say you have an allocation that is not traversing across loop iterations, and you can actually, instead of allocating on every iteration, you can pre-allocate one object and pretend that on every iteration it's a new object. I don't know, keep the zero initialization in the loop, but hoist the allocation and reuse the memory.
So that would be akin to a var definition outside of the loop and updating it on every iteration, maybe.
Yeah, so that's a different graph, and that one says I allocated ahead of time. Then there's a version that says I have an object that I'm making in the body of the loop, using it and throwing it away. So we looked at like billion row challenge, and one of the major things you do there is you recycle memory as you pull up a new city. If you make a string object and then probe the hash table, see if you have that string, you lost already because you made a new string object, probed the hash table. So you have to take a string-like thing, fill in the fields to make it a city name, probe the hash table, and on the 99.99% chance you got a hit, you just recycle that string-like thing with the next pile of bits from the buffer. And in fact, you can make your string-like thing just backs over the buffer, the giant buffer you're going. So this kind of a thing can be done in the sea of nodes, but we typically would consider using a peephole that did a local alias analysis effect, declared that the last use of that pointer ended at the end of the loop. Now I can hoist the allocation out of the loop. And we don't
Yeah,
have
yeah,
these
and I
samples.
agree with that. I think, the issue is that I can show you some of the discussion we had on this, where we had some graphs as well. The issue is that you need to be able to differentiate between the two, right? Where you need to know, okay, this new is in the loop, and then you do analysis and you hoist it out, right? What you don't want a situation is where you can't tell the difference. So if you didn't anchor it, then what happens is you can't tell the difference. You don't know whether
Right.
it was meant to be in the loop or it was not
Where
meant to
was,
be in
we
the
have
loop.
like 3
Yeah, and-
pictures in Discord.
So yeah, in Discord, I'll just switch to Discord and show
You can
you.
find it because I have one
Yes,
picture,
it's in the.
but not the second and the third.
Let
You put out
me
3
find
pictures.
this. So
Yeah,
here we are. So
I have
here,
exactly
there were
one.
3 sequences that I posted, right? And
Yeah, I'm looking for the 3, and I've got the 1, but not the 3. And it might not be going back far enough.
here we are, right? So these are the 3, right? So this one, the first one,
How far are you?
it's probably a bit too tiny here.
No, you're
The first,
okay.
you're okay. So the first one here is
Well, wait, no, go back
anchoring
to
the
your
new.
back to your classic program. So
Yeah.
hide the picture for a second. Nope, go back to Discord.
Okay.
Close that. Okay.
So this is the
don't
program,
move.
right?
Right. So here's the program. There's a struct S0. S0 ret is some new struct. It's out of the loop. In the body, we make another new S0, and we pick left or right. You're continuously making a new S0 in the body called V0, and then it's the return value or not if arg is ever 5 or not.
Exactly. So we are picking a specific one here of this loop, right? In the loop, the 5th value we are picking and we are returning that. So
Okay,
we have
so-
to be, this has to work
The key
correctly.
thing here, hang on, the key thing here is that there's a new in the body of the loop that has to stay in the body of the loop. You can't pre-allocate it in a general way. This program doesn't really make it force that you can't do it, because you could, you can pick two guys, and on Argus 5, you pick the left or the right out
That's
of the
right.
loop. But in practice, a little more effort on what you're doing with V0, it would not be able to be pulled out of the loop.
That's right. And then if you see this graph is pinning the new, just as I showed you in the other diagram, right? So then it's fine because everything is correct. You have a new outside the loop, and you have a new inside the loop.
Okay,
if you didn't do this, right?
Wait. I heard Arthur having a question, and I cut him off, and I cut you off. So it's Arthur. Arthur, catch your question.
So yeah, my question was a comment long ago that, okay, we can't do this allocation hoisting as a separate transform. What I was curious about, it seems like with these explicitly expressed dependencies.
Yes.
I was looking for, like, maybe there is a set of dependencies that we can express in the graph explicitly. So allocation hoisting just becomes a graph scheduling problem.
And
So
yes, Cameron, we have poor name choices because the example was just getting thrown out as fast as they could. Okay, so let's go on and look at the other formulations for the edges.
Yeah.
And we can kind of see what our space of choices of how you define things are.
Yeah, in this one, we removed that edge, right? And as soon as we do that, well, actually here we just have a memory edge. And in fact, this is not the one I wanted to show.
But leave it, and let's talk about this one. So there are 2 news. They both take a memory edge, and they both define it. So the top new is clearly outside the loop, and the bottom new is pinned in it because it takes a memory, produces a memory, which is cycled through the store and back around to being on memory, and cycled through the new and back around to memory. So the second one is pinned in the loop. And under the theory that we had a slightly different program where you used it in a way that couldn't escape anyhow, it'd have to be here, or else something would allow it to float out of the loop. If you didn't have either the control or the memory edge, you'd be allowing it to float out of the loop. So you need some edge somewhere. Okay, and then carry on, because we have a third one coming.
third one was really combining the first two. So maybe I'm missing, there must be another one which was before this.
No, I think we went back to chapter 1, and there's a bunch of them that were much further forward that we kind of settled in on whichever one we're going to go do.
Yeah, this one basically, is just a combination of putting both the mem and also the
yeah.
so this one is not good. I mean, not useful, but I don't know if I had a visual for the other one.
No, go the other direction.
Maybe this one.
No, this is got memory tall.
Maybe this one, yeah.
No,
Maybe this one, yeah.
If you,
So this one is basically showing without the mem or the control. What happens is the new is just floating around, right? And you don't know.
Okay, so
that is part of the loop.
So while looking at this, there's no memory at all. And there's an interesting question here. If we had fixed the no memory at all and you included memory, but the new didn't have any input pointers can float around, you can still imagine that the new's job is to name one of the infinite number of members of the struct v0, vx, y, and z fields. And because it's picking a name for any one of an infinite number, like the pre-existing in the X, Y, and Z slices, there's an infinite set of choices. New's picking one and handing it to you. You still need to know that you get a new choice every trip through the loop. So the second bottom new can't escape the loop in reality when you come to code emission. If, however, you had a separate, I made a pointer and I made a memory as two separate steps, then you could require scheduling, pull the new into next to the guy who actually makes the memory. And that gets into a graph that says I squished the new and the memory together. And that was a prior graph that we had done. So here is a version where we started with, hey, the new and the memory, and we're not showing the memory because the graph was stupid, fine. The new and the memory are split. The new is totally independent. It appears it can float out of the loop. There is a memory guy not being shown. It is pinned in the loop. It's generating a wad of memory that gets stored to zeros and load and store on it. It has to have a pointer to generate a wad of memory. The pointer points directly to the new. When you do code scheduling, you'd move that new next to that struct. Well, if the new is always next to the struct, you just might as well combine them.
But there is a problem, right? Because you can see here, the new was part of the if condition. So it should have been only if it's true that you do this new. But here, there is no link. So you can't really tell.
We're missing the memory. However, the memory is pinned in, the memory generator, the maker of memory, not the guy who gives you a pointer. However, the maker of memory is pinned into the body, then that's where the new also ends up having to go. And then it's no good to have them split apart.
Let me bring back the other one which has the memory, right? And this one, second. This has got the memory, right?
So imagine that memory edge.
But here also, if you see, the fact that the if conditions true and false have got no relation to this new, right? So you can't tell whether it was the if true branch or the if false branch.
That's a correct expression of the program, because you unconditionally made a new, and then you only conditionally kept it. 50% of the time, 90% of the time, the new that was made was actually dead.
Right.
So I claim this is a correct expression of that program.
It's interesting because
wait a moment. I have a question, but what if this if condition was checking, is it legal to allocate memory? Say, do I have enough capacity in free memory to allocate right now? Is it because you are essentially turning this into branching into masking, but I'm not sure if that's legal.
Okay, no, if the program wasn't expressed that way, if you express it that way, there are some tests, and under the condition of the test, I then do an operation, you would use a control edge to pin the new, which is what we ended up with. Although I claim we could end up with some memory only pinning, except it won't cover exactly your case of saying I have a new that is guarded by tests that I don't want it to bypass. So here's another way to think about it. I have a classic partial redundancy elimination issue. I have a three-way branch. I test. We all go to the same spot at the end. On 2 out of the 3, I do an allocation. The third, I don't. So if I just do standard common subject expression elimination, I would fold up the 2 out of the 3, and on one of the third paths, I do some work that I didn't otherwise do. If it's all adds or multiplies, no one fucking cares. The hardware covers you, whatever. If it's a new or divide by 0 or faulting op, you do care. And now you must be guarded by saying, even though these are identical in these 2 other paths, I can't do them because the third path might not do it and it might fail, and therefore the guarded
I
test.
assume you must have some way of expressing whether the node is speculatable, as in whether it can actually be something like the division or by 0 or just addition of 1 or whatever.
Right. So we ended up with it's not speculatable. It's not speculatable. It is pinned via control.
Yeah, I mean, that's what we've got now, but I'm not, to me, it's still an open question as to what we should do, because I'm quite happy that if we do want to go down this way rather than the control pinning way. So my concern would be, can we correctly create a schedule out of it, right?
Hey, Flavio, yeah, I'll send you, sorry, unrelated. Yes, Flavio, I'll send you a link here afterwards. Don't worry, sorry, back to me.
So yeah, so to me, it's still an open question as to what we should do. We've done it one way, but I'm not convinced that we've got it right. Anyway.
Go pull the other way up.
So the other way is really this one, where new is being pinned to the control, right?
Yeah.
And that is also shown in the Discord here. It's the first one, right? So here you can see new is pinned to the control. So if true, then only this new is happening, right?
Yeah.
Okay. So to me, it's still an open question. I think we need to kind of figure out what's the best answer, right? Because we're trying to do an educational project, so we want to be absolutely correct in terms of what should happen. Okay, so that's one thing.
No, I think it's not the right answer. Is not. We absolutely have to be correct because there is no correct answer. There are only choices, and you can now show people other combinations of choices and say, we went this way, but you could go this way, and maybe here's some trade-offs.
Right. We should put that discussion in the README as well. Yeah.
Yeah. Arthur.
Yeah. In theory, you can connect everything with control dependence and just end up with a classic ordered instruction sequence. And it's still correct. You can do it. It just has trade-offs that, well, now transformations are harder.
Right.
But
right.
maybe wait. I have some comment on that. But if made out allocation spin it on the while loop, maybe you can figure out which one you need. You can completely recycle on each loop. So if they're pinned on the control, how can you figure that?
So what I heard you say is, there's a common scenario where I have allocations pinned in the loop that I could lift out, and isn't this possible? And that one is yes. And there's peoples that do the trivial cases. So if we pick up a loopy guy, pick up the main one, not the one we're looking at.
But if you pin that on a control, you cannot figure that out, I believe.
No, you can.
Oh,
actually, okay, we can do it from here. So here I have a new under an if, and the if says if arg is less than 10. And then if we go up from the if, there's a loop header. So here there's something that says, I will like to try and do a transformation. And so I'm going to say, look up the control, up, up the immediate dominator trees is basically just follow the control edge until you fail because it's merging somewhere weird, and you find a loop. Well, wouldn't it be nice to move that new out of the loop? Can I move the new out of the loop? Well, what does the consumer of the new use? Well, one of them is a return in the bottom direction. That one just means if I did it ahead of the loop and I used it for the memory and then I exited the bottom of the loop, that's fine. So this is all people stuff now. I have another user, which is the store. Do I have anything else that says the new pointer himself escapes any other way? His consumers are a local store on the pointer's address field. He's not being stored himself. The new is not being stored into a struct. His exit is also just at the return. Therefore, that new is not escaping until the return. Now, at this point, I can have enough information that I could transform the code to say, I'll just move the new up ahead of a loop. And the actual program basically says that he makes a new object 10 times. He picks 1 and 5.
But
Or
that
on the
that is
fifth one.
that is figuring out how to move things out of the loop. But can you figure?
I'm figuring via a peephole that says, I find a loop on my control input. I'm going to swap you. I'm just going to actually lift. I'm just going to move the control input up to the loop's input, which would be control and start. And now when I do layout later, I'll put the new ahead of the loop, store it to zeros, or store the body of it according to whatever the store to V0 happens in the body of the loop, and then exit with the pointer on the return. So this is just a graph with standard graph, same graph layout algorithm happens. We'll fix this if I can get the new control edge moved up. And that's how other things that are not news get floated out of loops as well. As soon as they're not bound in the cycle of the loop, the layout algorithm will move them out later and you're done.
Yeah, I'm hoping we will get to those kinds of optimizations at some point. Right.
Yeah.
So, I mean, we are not there yet. So I wanted to cover a couple of other things. So this is one important point we had debated and discussed, and we've gone with a particular approach, but we need to kind of describe the other approaches as well in the documentation, right? And the couple of other things I wanted to discuss. So I'm going to switch back to IntelliJ and show you the diagram here again. Yeah, so here that's the peephole, right? So the peepholes, the obvious ones
pick the one on the left
because
it's easier.
Yeah, because we have the threading of the store based on the field, we can immediately see that this store of 0 is kind of redundant, right? Because we are immediately afterwards storing 1 into it. So by threading it on the field, we can kind of eliminate redundant stores, right? So that's a straight, simple peephole that falls out of this mechanism. Obviously, we are making trade-offs here. It's type-based, so it's tracking on a type and a field, and not based on individual object life cycles, right? So I guess that is something that is also possible, right?
I'm not certain what you're saying there.
So this is type-based alias analysis, right? So we are not tracking individual objects. If we had 2 vector D objects,
it is not.
We don't try to say, okay, do they alias or do they not alias?
Okay, I understand. So hang on. I would say it's field-based, which includes the struct, but it's not type-based in the sense it's not based on whether you're an integer or you're a pointer or you're a float or a string.
Right, okay.
Struct and field name.
Okay, but my question was that we are not trying to track aliasing between object instances, right, of the same struct type.
Yes.
So that is also theoretically possible, isn't it?
And it is. So because of the simplicity of trying to do the first cut here, all new vector 2Ds are all immediately confused with each other, unless you see a local pattern. So you can imagine the start was enhanced to include, somebody passed me another vector 2D unrelated to the one I have. I make a new one. I do some stores and loads until the new pointer gets confused with the incoming versions of vector 2D versus the new he just made. I know I'm looking directly at only updates to the new object I just made. So while I know that's true, I can peephole them directly. So in general, and this is what happens in C2 all the time. In general, you make a new object. There are a bunch of pre-existing objects floating around. The updates to the new object that happen in the constructor, both for C2's pre-zeroing plus always everyone else's constructor, plus the user's non-post constructor first hits, all end up using an obvious, I'm talking about the original vector, and there are no other users of it that confuse it. In particular, it's not stored or published, if you'd like. It's not published anywhere. Then I have no aliasing issues, and I optimize on the new instance directly by himself. Published instances are on their own set of things because they're looking at that address edge. Then at some point, I confuse the address edges because you publish. And at that point, I have to draw a line in the graph, which is not shown in this picture, that says, I don't know anymore. Now everyone who goes and says, go get me a pointer to a vector 2D and then do something with it, they get the confused pointer, and I can't tell anymore that I'm talking about the private instance or not, and we don't have a graph to show this. It's a very visual effect. It looks really nice in a graph. And that ends the, I have a private instance optimization setup. So mostly around the original first construction of a new object, you get a lot of good optimizations. Shortly thereafter, you publish, and then it's all lost.
Right. Yeah, so hopefully, we can eventually do those kinds of optimizations as well and explain them, right?
Yeah.
Okay, so the last thing I wanted to talk about is what we discussed yesterday and what fix I have done. And this is going back to our type lattice, right? So I'm going to try to summarize what you said to me, Cliff, but you probably have to explain it better. Basically, in our simple at the
You talking about
moment.
the pre-lifting thing?
Yeah, yeah.
Oh, geez. Yeah, I can try that.
Yeah.
All right, you want to go? Yeah, give it a go.
Yeah, let me have a go, and then you can correct me.
Yeah,
So,
okay.
in our type system in simple, we basically have a
Well,
lattice structure, which
don't you-
is
Do you have a picture?
how
for
do
the-
I show this? Maybe one way to show this is that let's
pull
have a
up
look
the
at
pull up the
let's have a
type
look at the
system.
type,
Yeah,
right?
just leave that on the left there where you see type integer, type mem, and the project file list. You don't even need the things on the right. You don't need the code. Just here is the set of things.
Yeah, so here we have the set of things, right? So we have type, which is the base type of everything. And then we have integer, memory, pointer, struct, and tuple, right? So the thing is that in our lattice, we had this issue originally that sometimes we didn't kind of think, well, sometimes an integer could either become top or bottom.
Aaron, not yet. We wanted to do field-based aliasing with structs first. So arrays are coming.
Okay, is that a question?
I'm answering quiet questions from the chat.
Oh, okay, right. So yeah, we will do arrays as well later on. But so what we found while doing this work is that we really need to kind of, if a value is in a particular domain, like if it's integer, or if it's memory, or if it's a pointer, or if it's a tuple, it needs to stay in that domain. It shouldn't escape that domain and suddenly become top or bottom. Top is like anything, and bottom is like everything, right? And that means that at that point, you've lost whether it's integer or it's a pointer or it's a memory or what it was. You've lost that information. So, and we need to kind of, we are now in a situation where we need to kind of say if a value is a particular type, it stays in that domain. It can still move up and down in the lattice, but it's got to be inside that domain. And that's the bug we were looking at yesterday. And the fix I made turned out, Cliff, that the issue was in the fee, right?
Well,
so as you mentioned,
you added a bunch of subtle, not complicated, subtle invariants to a lot of nodes, most of which already met those invariants. Fee did not. I think there's some other nodes that do not meet that invariant, but they'll have minor bug fixes in terms of code. But it's kind of a subtle invariant.
Yes. So in fee, the change I made yesterday was really to say, okay, you know what? If I have a fee, it could be a fee on integer, it could be a fee on a pointer, it could be a fee on control, it could be fee on a mem. What we don't want is the fee to suddenly become top or bottom, right?
Yeah, okay.
Excuse me. So what we do is we say, okay, if the fee is still being constructed, then take the greatest lower bound.
You have a more complicated piece of code here than is necessary by a fair amount. You don't have to do the null.
Sure, but let me explain. I understand. So let me explain at least what logically I'm thinking here, right?
Okay.
So the logic here is that if we have a single input, right, which is at the beginning when the fee is still not constructed, we will convert the type to the greatest lower bound. So that means it moves down, but it stays within the domain, right? Because it's the type's um, greatest lower bound, right? And if we have multiple inputs, then what we do is we say, okay, initially I don't know what the type is. If I see an input that I am interested in, then that becomes my first type. Any subsequent types, I do a meet. And if at the end, I find that the loop didn't even look at any of them, then I'm going to take the first one and do a greatest lower bound, because then I still want to stay in the domain, right? I don't want to escape the domain.
I'm
This
not
is the
clear
fix I did.
that this isn't buggy. But let's have that
Possibly,
conversation.
possibly. I'm just trying to explain
right.
the thinking behind it, right? Implementation could be buggy, but the idea is that you don't want to escape the domain you're in, so that when you are improving the type, it always stays within the domain, right?
All right. Do you want me to
yeah,
go
go for
here?
it.
I think there's some things that might help.
Yeah.
So I'm gonna take the screen share and find. Let's see if I can do this. Why is this guy? This and this, and that's probably too small. So I'm showing some pictures of lattices in the middle to sort of set the mental concept, and I'm going to go back around to what's going on here. So the idea here is types have a lower and an upper. Here's a chat. Let me go make sure that's sensible. Oh, got to run. I see you, Cameron. There's a lower and upper bound. So look at picture 3 is probably the better one. And in for simplicity, we've put a top and a bottom that's the highest and the lowest most point. So like in picture 3, there is a very topmost and very bottommost. That's top and bottom. And then when you run the algorithms that say, hey, I'm doing this improvement to a fixed point, the algorithms work because everybody moves up the graph or down the graph according to which way you're running the algorithm monotonically. They always take steps, either stay in place or they go uphill, or stay in place and go downhill if you start at the top and going down. All right, fine. But you could end up at top or bottom. And in particular, when you're parsing weird, bad test cases that start out by saying, if false, it's all dead. Now the code's all dead. You get in these funny zones where you've started at bottom because you don't know what comes around a back edge, but in fact, the front edge isn't legal, and you get an infinite closed loop that can't be reached kind of things. Under this situation, it's a simplistic classical fee would just say, meet over my live inputs. I have no live inputs. That meet is going to be top then. I'm gonna start at top because that's the high. I'm going to meet. That's going to make me fall, and I'll take the best answer I can get, which is the meet over all inputs. I have no inputs, so it's all top, and you get a top out while you're trying to lift. Okay, top's not any particular type. So if I go to picture 2 here, and I say the 80 up here is actually my top, and the 1's at the bottom, you can imagine each of the little square planes in the middle would be like all integers, and parallel to it, or maybe the side ones here, all pointers, and the next one, the 10, 30, 20, 80, or 60 parallel one is all ints, versus 2, 6, 4, 12 is all pointers, versus whatever. There's these parallel sets of mini lattices buried in the big lattice. Okay, why do I care about mini lattices carried in the big lattice? If I force the property that if I know I should be in a mini lattice, the ints or the pointers, and I force the types to always stay there, then I don't have to do a lot of testing for having types outside of the mini lattice, like top of the universe or bottom of the universe, the 1 or the 60 in my picture 2 here. Let me go get out of this and go share. And that lets me both keep the program's types more continuously correct, and keeps it from me having to handle all the cases where I have a full top and a full bottom. So let me try to pull up the whole damn thing here. Screen share again. Where's my Emacs? How about this? I haven't set for this. I didn't know you're going to try to go that one. That's a complicated one, and I haven't got even halfway there yet. 14. How about now? That's maybe readable? Emacs, why are you? Oh no, that's Zoom is like hiding the edge. That's what happened here. Hey, something sensible. Oh, it's chapter. 10 source main. I have an older version. I haven't pulled because we were just doing this stuff recently. So bunch of things. So here's the list of kinds of things that might be in the lattice. So top has top and bottom, has super simple types like control and X control. And it has helpers to help you sort out the other parts. Then integers have an integer top and an integer bottom and an integer 0, for instance. So it gives you a flavor of what's going on, plus any other constant and what that constant is. Pointers are going to have a special guy who's the null, and otherwise he knows what kind of struct he is and whether or not he might be null. So that's the kind of things you get out of pointers. Structs have a list of fields. Where's your list of fields in here? Right here. I don't like this implementation, but never mind. There's a list of fields. Linked hash map. Okay. And the struct name. So I'm struct flavored called person. I have name, rank, and serial number. Whatever. So these are kinds of things that show up in the lattice. So when it comes to running these algorithms, there's sort of two big philosophies here. One is I'm going to run the algorithm as it shows up on the theoretical slides I learned in grad school, or in papers, or in everybody's standard discussion. And that means I start at bottom and I lift to top, or I start at top and I fall to bottom, depending which way they're running. But you always have a bottom or always a top, and the code that does stuff with things has to deal with having a top or a bottom. So I don't know, pick somebody at random here, see if it does something useful. Yeah, this guy. Oh, you took out my int coverage piece because you didn't like it. Well, I think it should go in, and you're up against it for not having it. Okay, so here's a case where I'm doing a divide. It starts out by saying, am I an integer? So I'm not top and bottom. I've constrained myself to integers. If I've constrained myself to integers, I don't have to ask this question. Am I instance of type integer? I don't need that question because I'm always an integer on my inputs. And I'm only going to be an integer on my outputs. Okay, but if I'm not this, I'm one of these, either in either direction, then I run the general meet over my two inputs. So divide at A over B, but A and B are top or bottom, not any integer, then I just give you a generic meet answer for meet A, B. It's a kind of I'm handling this funny case where I'm not in the narrow domain. So that's the one that's conceptually easy to think about, that entire algorithm, because I started everyone at bottom, straight out of the parser, and I lifted you according to your inputs, and the lift continues up till you hit top, which doesn't generally happen on well-behaved programs, but I can make it happen if, like I said, I have an if false over a while infinite loop kind of crappy things. I can get crappy programs can hit there. Okay. The other philosophy is I'm going to just pre-constrain out of the parser all my integer expressions calculations to the integer domain, all my pointer calculations to the pointer domain, and the memory to the memory domain, and so on. And that means that any of these compute calls that are in a particular restricted domain can trust that their inputs come in that domain, and must enforce that their outputs only go to that domain, because the next consumer of it is trusting that they got the right domain. So I get this invariant that says every add, subtract, multiply, divide deals with producing something in the right domain, even if they might get crap, but they can trust they don't get crap in their input domain. So yeah, adds the same thing. They can trust their inputs are valid, then they have an easier time with it. But now I have to run that throughout every possible thing. And the one weird case, not the one, a weird case are feed functions, because fees do the same basic behavior, whether their inputs are ints or pointers or memory or whatever. So if I go look at fee node and I go look at his compute call, he has some funny games going on here. So let's talk it through. And this is not Debiandu's version. This is a prior version. This is the simpler version, but it lacks this property that we're talking about where I've pinned you within a certain domain of the broader lattice. So I have a region. I ask, do I actually have a region? Well, sometimes during the people optimizations where dead code is being nuked, I don't actually get a region. Or if I have something that smells like it has dead control, I'm going to say the entire feed isn't reachable. Therefore, its output is top. The most optimistic, best answer, because it's all dead code, and I don't care. The in progress test says I'm doing a loop. I have the reverse case. I have the input. Input 1 is valid. I don't have the back edge. What's in the back edge? Well, the obvious answer for the back edge is the worst possible answer. I have to handle the worst thing. So the easy one is to say it's bottom of the back edge. Bottom mean any type is bottom. I should just return bottom here and not return this widen thing. Now, Debian renamed that greatest lower bound, GLB. It's the same call, widen here, whatever. So in the nature of trying to pinch you into an inner domain, I ask the question, what is my input type? Oh, it's an integer or it's a pointer. So right here, or I say in1 of type, I'm really asking, what is the input type? Well, I do a virtual call on it. And if you're an int, I assume this is an integer fee, part of an integer expression. It must be pinched to the integer domain. Instead of returning the global bottom, I return the integer bottom. Or maybe it's a pointer and I return the pointer bottom. Or maybe it's a memory and I return the memory bottom. So on and so forth. Having decided I have all inputs, so I pass the in progress, I can now simply say, start at top, walk everybody, do a meet with a filter that says your input is dead. And the ni is unequal to this can actually be ignored. We don't need this test in there. It's a tiny, tiny efficiency hack. It doesn't change the typings at all. So the sort of the philosophy here is either I have something that's algorithmically matches the theory and is really simple in theory, and everybody has to handle their inputs being outside their expected domain. Loads getting pointers that are not a pointer, but they're top or bottom. Or an add getting an input that's a top or bottom and not some integer, which we're only doing adds on integers right now, so it has to be pinched there. And the other one is to say, everywhere I do a compute call, everyone trusts their input is correct, and they must constrain their output to be of the flavor of thing that they do. So you get this.
And the bug here was, that you sometimes in this loop, you will not meet anything because none of the inputs, the if condition.
Yeah, there's another way to deal with this problem that simplifies life. You're using input 1, but the time the fee is made into, the parser knows it must be one of these types. And you can just tell the fee, you are this kind of a fee.
Yeah.
So I would put.
Agreed. But here, like in the where you said where we start with top, the problem is in the loop, we may not hit any of the inputs because of the conditional check, right?
Right.
And so then we end up with the top as an output where we have lost the type information.
And that's what I'm saying. There's an easy fix. The fee, when it's created, gets told, hey, you're this type.
Right.
Because the parser knows the type. And the parser and the fee says, well, my type is this, and I have a final type, and then down here where I say I have no inputs, I'm actually going to start by saying this is type.dual, gives me the high version of that type, and if I have no meets, I've returned type dual, the high version.
Right.
So there is a way to do this where I don't need, and I said I don't need this piece here. This is like a thing. All I want to know is my region input is X control or not, and then I do a meet. So there's some version that says I don't have to have this loop be anything other than for I equals all inputs, just do meets. Do filter on a meet. And I would rather have that input as a, so we're talking philosophy of how to write the code here now.
Yeah.
Okay. I'm going to stop share, and then if anyone has a question, because that was probably not well expressed, because I didn't know, wasn't prepared for that one.
No, it was good. I think also we these are important topics in the whole implementation, right? So I wanted to make sure that we kind of describe them.
Right. Well, I would have said you're pushing for that version, and I would have said go for the algorithmic simple version because it just matches what you get on your slides you get taught in school. And raising the invariant to don't take the broad things, but pinch yourself to the legal domain does push this subtle invariant around to everybody. In exchange for you get a tighter, you never get this weird out of bounds situation.
Yeah.
Yeah, fine.
What will happen if the type is integer, but you're dividing with a type of long? Or I don't know, does the integer covers the int or long, or
right.
double? Let's say integer and double.
We don't have any floats.
Yeah.
If we get floats, then
You
we'll
have
have
to.
the parser will know that he's mixing ints and floats, and we'll have widening rules. And then a widening operator shows up. This is what do you do about ints and floats in general in every language, and everybody has a screwball answer. We'll do it the way C does it, something the way C does it.
The way the lattice is set up right now, it doesn't admit the types type top to be runtime representable, like a Java new object. This is
a type, yeah, a global top or a global bottom is not any runtime value. That is correct.
Okay.
You shall not have them. If you're globally top, your code is undefined, and it's probably only can happen if you're dead and it's gone that way. And if it's bottom, you have mixed things that are not legal to mix, and that's a type error, and the compiler should toss you out as broken code.
Yeah, I like that. I like that too, not admitting the object type at runtime.
I'm sorry, option
Is
type?
bottom necessarily that you're broken, or just that you're doing something unsafe that you shouldn't be doing? So like if I cast a void star and then I cast to something else somewhere else, that void star is kind of the bottom type because it's the pointer to literally anything.
No, it's not a bottom type.
It's the top
pointer. It's a pointer to anything. That is not a bottom type. So bottom type would be I cast hex 1, 2, 3 to being a pointer, except that the cast operator would declare that I got a pointer out of it. So if you treat hex 1, 2, 3 as a pointer, that's a bottom operation. You will get a bottom type out. If you cast it, the cast gives you just says you're the good type. You're a pointer when you get done.
The way I think of it, is like I could be wrong here, but the way I think of it is like when you have top, you are saying that I don't know what the value is, right? Then say like looking at integers, then you get the middle where okay, I'm this integer, I'm 0 or 1 or 5, or then you get bottom. Bottom is where you're saying I am all integers, all possible integers.
Yeah.
Right.
That suits as long as you're categorizing values, but if you're categorizing types, there are some tricks there.
Oops.
At least that's my opinion.
Right. Top is I could be any one particular type, and bottom is I am simultaneously all possible types.
I would the equivalent I draw is the Java new object. Java object type is the top runtime representation of a top type. So it could be anything. So it's just an object. So one question would be that let's say Scala, if you assign a value throw new exception, the type of the value is nothing. So how are there if you are going for expression oriented design, then every expression must have a type. So if it's an assignment, then it's a unit. If it's row exception, then it's nothing. How can this be supported or can be supported? That's
Sorry,
one
I
question.
didn't listen because I was typing an example. Are you asking a question for me?
A general question. So for Scala, they're expression oriented. So if you assign a value, the expression throw new exception, the type of the expression is nothing. So
if the expression throws an error,
yeah,
an exception.
it's val hixix will throw new exception. So So the type of the X
Right.
is nothing. That's
Right.
that's a sneaky way to type expression. That's
In what I'm doing in the sea of nodes,
Mhm.
the throw an exception is control flow,
Mm.
and there does not exist a consumer of the value that you are trying to define an expression for, and so it becomes a non-issue.
Mm.
I don't have to game a type for it because it cannot be used because you
Mm.
threw it.
Mm. Mm. Okay.
Hey, Heinz. So in the middle of the code block,
Okay.
I showed an example where somebody said, hey, what about using integers and pointers and when is an error? No, the example I showed doesn't have a cast. So let me show another example. This is, oh, Aaron, you're asking this one. This second piece of it, I would have a cast node in here. And the cast node would be included inside of it. The type it's going to get would get encoded inside of it. This cast result, you know, in SSA form would now not be an error type. It would be a pointed object in the Java domain or pointed void in C domain. It's not an error. You have told me that it's okay to do this cast. And a typical for things for look like cast for me is I include a control edge. So the cast is pinned behind whatever test you have to guard the safety, and you're doing an unsafe cast. And you told me to trust you, and simple won't allow this, but C would allow this.
Yeah, but if you cast it to a void star, then how can, if you intermix that with the other values, how can figure what type should be? What the other values, their types, what
Well, as soon
would
as
be their
you,
types?
yeah, if you have a thing where you're mixing void star with other types, you'll get the most generic type out of it in the land of a well-typed system.
Okay, unless you explicitly cast it back to something known, and
yeah, right, you have
and
to
your
cast it.
input should be trusted. Okay,
Right,
that's
right.
fine.
So I could have a var pointer 2 is pick at random from my evil pointer I have up here and a real pointer I got from a string ABC. Okay, what is the type of pointer 2? No, pointer 2 is void star type.
Okay.
To me, you know, like what we were discussing before is like once you have a pointer, you stay as a pointer unless somebody casts you, right? So that's different. But if you're not being cast, then you want to stay as a pointer. Either you know you're a pointer to a specific type, or you say, I don't know what the type is. I'm any pointer, right?
The strategy we're using in simple is it's entirely type safe and we don't have to answer these questions. You can't cast. No casting. There's no inheritance right now, and therefore there's no subtype, supertype, and there's no casting. Problem solved.
Problem solved.
Yeah, when we get to super subtypes with inheritance, we will have casting, and they'll have to be guarded by a test. And then the cast node will take a control and do a cast. And I casted a pointer 1, 2, 3. I mean, an integer 1, 2, 3 to a pointer, but really a cast from animal to dog. Same kind of behavior. Trust me, this says the cast, but the cast himself says, but I depend on this test. The test is telling me that it's okay. And that turns into a runtime.
So if it
test.
can't prove the cast is safe at compile time, it will insert a runtime test.
Yeah, that's
okay. That's a
the
language spec, right? So there's a couple ways to do that. One is I'm Python, I'm going to cast and then fail at runtime. Another one is I'm Java, I demand you put a test at runtime, and then whatever the else clause in the runtime is whatever happened. That'll be what happens if you fail the thing, right? That's, you know, if X instance of, I'm sorry,
you mean to force the user to explore what happens.
Right, and here I have a dog here. Right, the user has to explore what happens.
Can you scroll down? We don't see the code.
Yes,
At least
sorry.
I don't see it. Yeah.
Probably.
Yeah, there's something kind of elegant about a cast else statement.
Right, it's a cast else, and now I can't do dog things. I have to do animal things only. Right, I don't get the dog. Up here in the dog part, I can do dog things. Dog is a valid thing, and I can do dog things.
Yeah.
And that's, yeah. And that's how
and normally the else would have, if you want to use the symbol after the if,
Yeah.
it needs to be defined on both branches.
In you know, you look at the Java model here. We can do this the other way around. Here, if not animal of dog, I'm going to do animal things up here.
Right. My thought was if I want to be able to use that symbol after the if statement. So I want it not to go out of scope as soon as the if block ends.
You have to unify them. So
Yeah.
Then I need to have it on both branches.
Yeah.
But if one of
that's-
the branches returns, then I have unified because return unifies with anything.
Yeah, that would become infinitely more complex if you have a partial, let's say, a structure of types. You have to unify all the branches and figure out what the common.
So I'm showing
would be.
like Java things, but AA has exactly what you're talking about, and it just
Right, because usually my result is going to be if try to do this cast,
yeah.
else return an error condition type.
Yeah, but
and then I can keep going with my function without needing to get a pyramid of doom.
But that's Java
because
right
I bailed.
That's
the Java thing right here. Return animal thing, right? If not animal, instance of dog, return it as an animal. Otherwise, I can do dog things. And dog is a variable. It's allowed. No unification, just control flow. Does that make sense, Aaron?
Right. My question is, why is it still in scope later?
Dog down here? And down
because
here,
your if ended.
The dog is in scope in Java even. It's in scope because the test says if not animal instance of dog, do this other thing below there, and it returns. It goes away. Below that, it's now dog remains in scope.
That's kind of a trick, because you either have the general instance or you have the specific instance, but either way it's some kind of animal. So this would be typed as at the worst case as animal. So
well, the dog is typed as a dog, and the trick is that you never get to the dog side of things.
What would happen if you
What would happen if you didn't have the return? Then
then Java would disallow
by
you.
the time you ended the if, you would no longer have the context of which side you branched.
Yes. So if you don't exit, then Java will say, no, this is an illegal program and you have to unify, and you don't get the name dog is out of scope. Below.
Right. But this unifies fine because return unifies with anything, because
it doesn't do any unification. You say unify, there's no unification.
If you assign that to a variable, what would be the type here? So provided that it has to be a ternary expression. So if you do Java,
well, no, then you're going to get a unification.
Yeah.
If
so
animal,
if you're using that
dog, now I'm going to do something with dog. Dog and whatever I'm going to do with dogs, I'm going to take it as it stands. But now what I put in this else clause, and that becomes a unification.
If it's an animal, so if
right, my choices are default dog or bail, essentially.
Right. Yeah.
So or the trick you use it's an animal. Some use it from some prior animal.
Yeah, but if it's an animal, then the value for X is animal, not dog, and I cannot do dog things.
Yeah. You cannot use it as a dog later.
Yep.
So that was my question. Okay.
Yeah, cool. Yeah. And that's like this is like Java now. Like AA does this as well, and I'm certain other languages do this as well.
So they have to do it.
Not a hard thing. And it's just, when they had the if test version, I'll repeat it down here. It's just, did I leave scope or not?
I mean, it certainly smells better than throwing because you tried to cast and your cast failed.
Like this. You can have any kind of thing you want as long as the parser can verify that the control flow never exits down to the do dog thing. So you are pinned or defined to be limited to what the parser can do analysis on that says that I didn't escape. So that in AA, I'm going to allow you to have sort of any arbitrary control flow there. And if he declares that you've always exit before you hit the do dog things, I don't care. In the land of Java, you are limited to saying, I can tell that I'm returning. So if instead in Java I said if true return, and then I got rid of this other thing, the Java compiler says, no, I cannot tell. I'm not smart enough. So then I cannot tell, therefore this code is illegal. So that's illegal. Even though it's obvious to us that you never get down to do dog things if you're not a dog. So it has to be textually available to the parser, which means it has to end like in a return. You can have other statements here. So I say statements or block, right? Statements here is okay, but then I need a return animal. And that's the parser is doing a limited amount of type inference and discovering that he thinks there's no path to do dog things without going through the instance of test. So that code's okay, but his knowledge of what he means to be like how you can get there is limited to basically pure syntax observations.
Okay, cool.
All right. Well, are we new topic time or are we done? I'm just throwing it out there. More hacks.
In Java, if you're exhaustive and you've said, is it a dog?
Right.
Will it be a cat on the other side because you've said exhaustively animals are only dogs and cats? Or will it just be animal on the other side?
The Java parser, as of some later version, somewhere around 2021, lets you seal classes. Sealing means there are no subclasses across all of them. He will then count the finite list that is in the sealed set in a switch statement and indeed declare that you get exactly everybody.
Okay.
So under some situations, yeah, they'll say there are two animals, dogs and cats. You said if dog, and now I guarantee it's a cat. But it's a syntactic change first that says animals are only cats and dogs. And that's what sealing does. Sealing a class.
Do you plan to have sealed classes in AA?
Probably. It's an interesting domain. It's basically what an enum is. There's a top level enum declaration, and there's a list of choices. Hey, your enum is cats and dogs. Hey, your enum is E no interrupt, E into file, E disk full, E da da da. I have 27 enums. Okay, I do. Well, there's an exhaustive list.
It does feel a little cleaner to me to have some kind of variant as a distinct concept from struct. It's like, no, this is a variant. It's exactly one of these things.
It's exactly one of these things. Yes, yes.
And then you don't need to think about sealed classes as a property of a class. It's just, is it a variant?
Yeah, it's just a variant, right. And I've worked with like Elm has this nice variant variety of things as well. So I've worked with these kind of languages before, and that piece works out well. The switch makes sure you cover all the pieces. The virtual call makes sure you cover all the ground. You can still have default cases if you have 27 choices, but you're only excited about one or two, whatever.
Yeah. I think Rust handles this well, although it's a little jarring that they've spelled variant enum.
Well, Java said sealed classes, but they also have enums. But that's history. That's because they're trying to say the user wrote this as a class and a set of classes, but then they wanted to declare that that's all of them, but no syntax change. So we have to do something. So
that's why
the Rust enums were confusing to me when I was like, but I don't understand how you map all these things to an integer.
Yeah.
And then someone was like, no, it's just a variant. And I was like, now it all makes perfect sense. Thank you.
Scala 3 just combines the concepts and they call them enums. So they discovers the two cases.
So there's something that says that the name choice, so to Simon's point, there's some name choice, it matters. Enum apparently was a bad name choice for Rust.
I think it's the opposite. I think because Rust chose enum, that the concept that is in my head as variant will be referred to as enum by future generations of programmers.
Well, so that
which is fine as long as they know what it means.
I would call that enum as well.
But you know,
Enumeration. A
didn't this
list
come
of finite
didn't
size.
this come from algol actually? It's not new, is it?
Oh, it's no
What
the
did
concepts.
algol do for its enums? Were they like converted to an integer, or were they some fixed set of cases that could potentially have their own payloads?
Oh,
I'm just trying to
algol.
find the document. There is a description of algol 68.
Surely algol came from the pre-CLAN, and an enum would be just an integer, a closed set of names for integers.
Someday
let
I've
me
got to sit down
find
and read the algol 68 spec from top to bottom.
let me find the link. I will post it. Just give me a
Okay.
second.
But that concept of named integers and a finite list of them has been around, yeah, for a long time. Yep. Let's see, I had started when I was 8 or 9 on Fortran 4. No enums in Fortran 4, but I knew that concept before I would say 10 or 12. I knew about what enums meant. That's pretty scary.
So I'm just posting a
10-year-old.
link. Just give me a second.
I just saw it in the doc. I'll scroll up here. Yeah, toss it in the doc. GM knows we have some discussion in the middle. Oh, all right, Theodore. I was going to say there was some big discussion, but a lot of it was like lattice theory of binding. I would have said separate from memory presentation. There was this lattice theory.
We missed that, so sorry.
Yeah, fine. I wasn't paying attention.
Me neither.
Yeah, right. Exactly. No problem.
Okay, links. Just add it to the links. Yeah.
Yeah, just added the links. Yeah.
Okay. Can you see it?
Oh, it'll show up. I see it on the. I mean, I see added there. Yeah. Yeah, there it is. And then now it just.
And then if you look at, there's a description of. Oh, is this the right one? Sorry. Hang on.
Don't worry about it. You get close, and then people can hunt more. It's not like it's hard to hunt for algol essays in computer science. No, you've got some general outer contents. Contribution to the development of algol, page 31.
No, maybe I pasted the wrong one.
Yep, might be. All right, I'm gonna let you sort
These
on
are
that.
all classic books, so this.
Oh yeah, right.
What's interesting is that a lot of the ideas we have in Rust, I mean, especially with enums, came from algol.
Oh, a lot of this stuff came from algol. Yeah. No, first real thought
I'm
put
going to
into a
replace
structured
that
programming
link
language.
with another one. Okay.
All right. Anything else? I'm gonna cause wrap up here in a minute.
My professor always used to say algol 68 improved on all of its predecessors and most of its successors.
Fair enough. It got people thinking the right way. I think that's reasonable.
So there's a description of, I think it's called enums, but I'm just trying to find it.
Yeah. I'm gonna say we're not gonna wait for you to find it, but throw it into the doc. The doc won't close when the session closes here. I have to have some video presentation that's worthy of watching you.
For what it's worth, algol 68 had tagged unions.
Tagged unions? Yeah, okay. Oh, really?
That's kind of close. It's actually, I can post it.
No, tagged unions are all but the identical.
Yeah.
Yeah, enumerated types are just special case where you only have units as each of the member.
Right.
What are the other historical languages that you encourage people to look at when thinking about how they want to design a language?
Oh, gee.
You've mentioned Forth a bunch of times. We've mentioned Lisp on and off.
Yeah. I hate to say it, but COBOL has this fantastic, amazing property that beats everyone else, and that it was alive in the early 60s.
I would have almost said Modula 2 for modules, but today I would say better look at OCaml modules.
Okay.
No, but historically, but that's in the
But historically, yeah, Modula 2.
Historical, right.
Yeah.
I don't know. Let's see. A bunch of people claim, a lot of these research languages that never hit it off brought new concepts in for the first time. But now, is it worth to go back and reread them, or just go read the modern variation in the first place? So I think Forth does something that nobody else really does well to this day. And that's that you hands-on immediately interact with hardware on embedded systems where you have no other support whatsoever. You need under a kilobyte, and you can type it in as literally hex on a brand new chip that has no other things and get a language running. That kind of a low overhead to get started is really useful. And it's a REPL all the way. Algol had a lot of good history, a lot of good ideas they brought forward, and then languages improved afterwards. And a lot of languages, as you pointed out, did not actually improve afterwards. I mean,
Well,
we can pull up Prolog.
The funny thing
know.
is, so I just refreshed my memory. So it didn't call them enums, it called them discriminated unions, right?
Yeah.
And so
type
that's what
unions. Okay.
enums are in Rust. What's funny is that C
Don't-
was derived from Algol, but they kind of lost this idea of discriminated unions. They just had unions without the type
Oh,
field.
C. Yeah, you could.
Yeah,
you
I
would
think
add
discriminated unions are a lot more powerful.
You would add.
Yeah, because in Algol, 68, if you look at this document, it gives you the syntax where you can say width, and then once you are inside the block, your union is of that specific type, subtype.
So C said for performance, you will understand yourself how the union is discriminated, and we don't demand that you consume storage to discriminate in case you have a way to discriminate without any storage. You're
Yeah,
allowed.
the C argument was put a type field in your struct.
And then if you didn't, you put a type field in. Yes.
I thought of one more language, CLU or CLU, if you remember Barbara Liskov. One reason I would look at this is actually it had generics, which is amazing for language that appeared in 1975. And not only did it have generics, they were actually type checked. So that wasn't in many languages that adopted generics later.
Right. Sure. All right. Well, I kind of think I mean, it's a fun little topic, but I'm not super excited. And my wife's back and it's lunch, so I'll take final call for questions, but I'm gonna wrap it up here.
Thank you all.
Yeah, thank you all.
Nice.
All right,
Thank you.
till next week. And thanks for the presentation, Nibyendu.
Yeah.
Cheers,
Bye.
bye.
Goodbye.